So our topic is the order of an element of a group. So simply define this one. Suppose G be a group, uh, group, and you take an element A that belongs to group G. Okay. Now the order of an element. Our topic is the order of an element of a group. So G is a group. I am not specify the binary operator here. Simply G is a group with respect to any binary operations, and A be the any element belongs to G. Okay. And one more thing, the E is the identity element. Identity element. Identity element of G. Okay. So now, what is the order? The n. Suppose an integer, a positive integer. Simply write a positive integer n is said to, or should not, at least positive integer. Least positive integer. Okay, n is said to be the order of A. Okay, that belongs to G. If A to the power n is equal to E. Is it clear? So what is the order of an element? Suppose E be the G is any group with any binary compositions, and E be the identity element of that group. Now, if you are considering the any element A that belongs to G, then what should be the order of that G? So order is order of any element. It is a positive integers, but not all positive integers. The least positive integers which satisfy this condition. Okay. So for example, I'm just taking, and it is denoted by or order of A is equal to n, whatever mean. If this, it is the notation, and this is the definitions. For example, what is take? Uh, Suppose I am considering Z, okay, fourth root of unity, 1 minus 1 I minus I, okay, and obviously Z multiplication or simple multiplication, Z into, this is a group with respect to ordinary multiplication, with respect to ordinary multiplication. Then question is find the order of each element. Okay. Find it. So first of all, we should check what are the uh, what is the identity element of this. What is the identity element of this? Hmm? What is the identity element of this one?
Sir, 1.
1. If you are 1, because if you multiply any element with 1, it gives you the same element. So 1 belongs to G, be the identity element. Uh, identity elements. Okay. Now, what are the order of each element? And let us find. So, what is the order of 1? So, you see here 1 to the power 1, that is equal to 1. Okay. Now, 1 square is also 1, 1 to the power 3, that is also 1. But as per the definition of the order of an element of our group, this exponent or this n should be least integer, n should be least positive integer. So positive integer, it starts from 1. Okay, so the order of this implies, you can say the order of 1 is equal to 1. Next, come to the minus 1. What should be the value of n here, so that it will give you 1? That means with respect to the ordinary multiplications. So we know that minus 1 to the power 2, that is equal to 1. Okay, so you can see order of minus 1, that is equal to how much? 2. Similarly, what are the orders of I and minus I? So what should be the value of n such that I to the power n is equal to 3, and that n should be least, and minus I to the power how much? Tell me. So that the order of, okay,
So 3.
how much it is? If it is 3, then never you will get some integer.
4, sir.
It is I square, it is 4. Okay, so this is equal to 4. And what about this?
2.
2. 2, that means minus I to minus I, that is the I square. This will give minus 1. If you are putting the 2, minus 1. If you put 3, then you will get I. Then again this should be 4. So this is 4. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now I am giving you a task. Try to solve this one. Question. Question is what should be written? Prove that and with respect to any binary composition G, A square is equal to identity. Okay, then G must be an abelian group. Prove it. Try for this. That means each element has order 2. Each element has order 2, then this must be the abelian group. But not necessary. Because I am writing here if, not if and only if. Okay. So prove that if for every element A in a group G, A square is equal to A, then it is a abelian group. But if it is not true, in that case also it is a abelian. Okay. And the previous example, in the previous example we see that some element has 4, some element has 2, and some element has 1. In that case also it is a abelian. Prove it. A square, that means ordinary multiplication here. A square represents ordinary multiplication. So how to prove it? our binary composition this. I'm just give you the hints, but you have to prove this. Let suppose let AB belongs to G with respect to some binary operation this. So then by G is a group and AB belongs to G. So then this must also belongs to G. Okay. So if this belongs to G, okay, and for every element, that means this is also an element. This is also a element of G. Then according to our question, we may write it like by question, this is an element, the square of this must be E. What is the E? E is the identity element. Okay. So you may write it like A asterisk B and A asterisk B, and that is equal to E. Is it? Is it clear or not?
Yes, sir.
Yes, sir.
Now what we have to prove? What we have to prove? We have already proved these problems in previous, suppose 1 and 2 class, suppose in the third class of this group, we have already proved this problem. Since it is related to the order, and that's why again I just recall these problems. You can see the previous notes, there I have proved this problem. How to solve it? So one more thing, suppose A into B is equal to E, then what about this B? Is there any relation between A and B if the product of this is E? Hello?
Yes, sir.
What is the, if A asterisk B is equal to E, then is there any
Sir, A
relation?
star B is also A star B inverse.
Hmm? What is the relation between this A and B?
Sir, B is the inverse of A.
B is the inverse of A. That means A inverse is equal to B. You can write it like this.
Yes, sir.
So what is A here? This is your A and this is B here. So you may write it like A, the inverse of this is equal to A star B. Am I right here?
Yes, sir.
Oh,
Yes, sir.
see the previous notes. Okay. Now this equals how much? Again we know that this B, and we have already proved this one. Ultimately we have to solve that B inverse is equal to B. Okay. Proceed like this. Proceed it to get B inverse is equal to B. Once you get B inverse equals to B, then you get it is a abelian. B inverse equals to B, that means what? A inverse is equal to A and B inverse equal to B. B is the any element, and what we see here, okay, B inverse asterisk A inverse equal to S to B. So in this place we should write the B here, and in this place we should write A here. So B asterisk A equal to asterisk B. That means it is a abelian. So check this one. I am not going to prove this one. We have already proved the same problem. Okay. So now Come to the other problem, that is the coset. Okay, so before come to the coset, we come to the cyclic group first, and then we have a quotient group also. So come to the cyclic group. What is the cyclic group? Uh, cyclic group. So it is also a group, but particular type of group. How to write it? A group is it is the definition. A group is called cyclic. A group it termed as like the group G with respect to any binary operations. Okay, is said to be cyclic. Okay, if some A is the any element belongs to Z, there exists an element if like this, group G is said to be a cyclic if for some A belongs to Z, every element X belongs to Z can be expressed in the form of where n being some integer. Okay, and the element A is called the generator of G. Okay, and in that case G is simply denoted by, and you see here I am writing here the some integers, but in case of the order of an element of a group, we specify it is a positive integers. Okay, some integer, that means it may be negative, it may be 0 also. Okay, so generator of G, and in this case we denote G is equal to like this A. So A is the generator of G. That means in G, why it is called generator? Because by means of A, okay, or with the help of A, any element can be expressed in the form of A to the power n. That means any element of G can be expressed in terms of powers of A. Okay, if it is possible, then G is said to be cyclic. It is not valid for all group. Okay, it is a special type of group. Okay, where any element of that group can be expressed as the powers of, okay, powers of one of the elements. And you can see later I will give you the two examples or one examples. There you can see that we have more than one generator of a group. We have, for example, simply if you are taking the same example, I am taking, is it clear what is the generator? Cyclic group?
Yes, yes, yes.
Cyclic group, that means any element of that group can be expressed in terms of powers of other element of that. A is the any element of this G, and then any element X can be expressed. That means any element X can be expressed in terms of this. Okay, and when n being any integers, it is not restricted to the positive integer. Okay, So now, example, I'm just what example you should take? Example, take the same one. Suppose G and simple multiplication, and that is equal to 1 minus 1 I and minus I. Okay. Now, can you identify what is the generator of this? Can you identify any one of the elements? That means by means of that element,
Minus
can you
1.
Minus I.
no. This
Minus
and this,
I.
listen, this and this never be
Minus I,
generator.
sir.
Okay, this and this never be a generator, because whatever may be the power of 1 or minus 1, you never get I. Okay, so leave these two. Come to the I. If you take the powers of I, then you can get 1 and minus 1. So there is a possibility of this or this. So let us check it. So you see here, I to the power 1. This equals to how much? I. Okay. I to the power 2. That's give you what? Minus 1. So you are getting this element, and I to the power 3. This will give how much? Hmm?
Minus I.
Minus I, and I to the power 4. This will give how much?
1.
Okay. So you are getting 1 minus 1 I minus I 4. So you may write G like this. I or I square, I to the power 3, I to the power 4. That means you can say G is a cyclic group I, or G is a cyclic group. Is it?
Yes, excuse me, sir.
Yes. Yes.
It means the generator should be contain all the elements.
Now, generator should be the element of G, first thing. And any element of G can be expressed in terms of generator to the power n. So here I is the generator. Generator, that means it can generate any element of that G. Is
Okay,
it
sir.
clear?
So every element that will be
Every,
contained.
yeah, every element.
Yes.
Okay,
Yes.
every element. So now any other, so you see here, and let us see minus I. Also consider minus I. Minus I. And what about this? Are you getting the all the element in powers of minus I? Hmm? Let us try this one.
Yes, sir.
So just tell me, I minus I to the power 1, that is equal to minus I. Next, minus I
Minus
to
I
the
to the
power
power 2.
2.
2. 1. Minus 1.
So it will give minus 1. Okay. Minus I to the power 3, it will give how much?
I.
I. Good.
Minus I to the power 4. 1.
So you may write it like this. So G is equal to minus I to the power 1 minus I square minus I cube and minus I raised to the power 4. So all the elements of this can be expressed as a power of I minus I. So again G can be written as cyclic group with respect to the generator minus 1. So what is here? G over here and G over here. So generator is not unique. We may have more than one generator. Is it clear?
Yes, sir.
Now I think you can solve other problems also. So I will give you some examples and try this one. So suppose Z is the set of integers, okay, integers, and A star is that is equal to ordinary addition, okay. Then we know that Z this is a group, okay. Then is it cyclic? Is it cyclic?
No, sir.
Cyclic. It is cyclic. It is the assignment. Okay. It is a cyclic. So what you write it? You can write it like the I am just telling. Tell me any element.
1.
1. 2. 2 is the any element. 1 is square. 1 plus 1. This square represent not the multiplication only. This square represent the asterisk. Here asterisk is plus 2. Similarly, 1 to the power 3. So 1 is the generator. Is it? Similarly, you can write the minus 1 also. By the way, it is your assignment. Leave it. Now, next question is, it is a question I am not examining. Question is, prove that what do you write? The cyclic group, and every cyclic group is abelian, right? Okay. So prove that a cyclic group is abelian. How to prove it? First come to the what is the definition of abelian. Abelian is AB equal to BA. We have to prove like this, and it is a cyclic. Cyclic means what? Cyclic, that means this is generated by some elements of G. So if you solution, if you consider like this, what you write, let G this asterisk, okay. Anything you can write it, or G asterisk, or simply.
Sir, your voice, sir.
Now
No, sir. अभी भी इसे बहुत low है.
so probably there is a net problem in this side. इधर काफी problem आ रहा है net का.
Sir,
So now, yeah.
Sir, you're audible.
Okay. So now suppose G be a group, okay? G be a group, and of course the cyclic group, okay? So write the cyclic group. G be a cyclic group, and once you say that it is a cyclic group, then definitely we must have some generator also, and A belongs to G with the generator of G, that is G is equal to B. Okay, so you may write let again let, and B and C are the two elements of G. Suppose B and C, and since A is the generator of G is the cyclic group with A as generator, so therefore any element of G can be expressed as the power of R. So you may write it like that: B is equal to A to the power suppose P, and C is equal to A to the power Q. Can you express BC in these terms?
Yes, sir.
So now what we have to prove, that AB equal to BC. So that means now we should write the BC. That means B asterisk C here. Okay. So what should be? Well, this is A to the power P into A raised to the power Q. That is equal to A raised to the power P plus Q. That is equal to A raised to the power Q plus P. That is equal to how much? A raised to the power Q, A raised to the power P, and A raised to the power Q equal to C, and this is B. So what you are getting? What you are getting? BC is equal to CB. So therefore BC is equal to CB, and therefore G is, and B and C are the any arbitrary element. So G is an abelian group. Is it clear?
Yes, sir.
Yes, sir.
So that means if a group is cyclic, okay, then it is abelian. Okay. Similarly, um, you can see that the 1 omega. Another example. This is your assignment. This is your assignment. So that G 1 omega square is cyclic. So it is a cyclic group. Okay. This is your assignment. Is it clear?
Yes, sir.
Yes, sir.
Now
Yes.
come to the coset. So first the order of the elements, okay, and then the cyclic group one by one. So now come to the coset. What is the coset? What is the coset? Very important topic, because what is the importance of this? Directly the coset hasn't any direct applications, but to prove many problems, okay, we use this. So like you can treat this like a catalyst. So when we are going to prove some theorems, we take the help of this coset. Okay. Now what is the coset? Suppose GB a group and HVNE subgroup of G. Can anybody tell me what is the conditions that H be the subgroup of G? List one. Suppose AB belongs to G, okay? Then sorry, H, and that H is the subset of G. Then under which conditions you can say that H is a subgroup of G?
Sir, list condition, sir.
List condition.
Sir, if A belongs to H and B belongs to
B
H,
belongs to H,
then A into B inverse, A steric B inverse belongs to H.
good. So keep it into the mind. Okay. Whenever we have to prove that H is a subgroup, okay, we try to solve the problems using this theorem. Because here we have only one step to show that H is a subgroup. Otherwise, you have to consider all the four conditions, three conditions in fact: closure, identity, and the inverse. Okay. So it is a G is a group and H is the any subgroup of G, and A belongs to and A be any element of G. Then we define a set. So what is the difference? H A. This is simply notation. Okay. So what is the meaning of this? HA is equal to H into A. Actually, here, although we are writing H into A, but practically it is H asterisk A. Okay. So HA such that H belongs to H, small h. So we consider this set, and this set is called right coset. A belongs to G. A belongs to G, and we consider a set such that we are taking the binary operations of each element of H to A and construct the set. That set is called the right coset. Right coset of H in G, generated by which generate this coset? A. This A generate this coset, so it is A belongs to G. Is it clear? What is the
Can
right
you
coset?
Yes.
explain it once more?
Okay. You see, G is any group with respect to any binary composition, and H is a subgroup of that G. Now consider an element A that belongs to G. That means A belongs to G. Okay. Now we consider a set denoted by capital H into A. Okay. Actually, it is asterisk, not A. Capital H into A. And what are the elements of that set? That is small h into A. Okay. And this H belongs to this subset. Okay. That means this is the product of elements of H and the element of Z. Okay. And this A, sometimes this A belongs to H also. And simple example is the identity. So this set is called the coset. This set, it is a set. This set is called the coset. And since we take the post multiplication of A with H, that's why it is said to be right coset. I am taking A on the right of H. So it is said to be the right coset. So what is the right coset? It is a set. Okay. So a special type of set. What is that set? Whose elements are in the form of HA. Okay. and A belongs to G and H belongs to the subset H. Now is it clear?
Yes, sir. So here A, B, and any element of G means, are we taking a particular element or the all element of G?
No, right coset generated by A. Similarly, you can take the any element. If you are considering the B, then that is generated by B. Okay. If it is the
Yes.
finite set, you see here, how many coset you are getting like this. If you are considering the finite set, which is, suppose in our previous examples, in the we are taking fourth root of unity. That means the order of that group is 4. We have only 4 elements. Okay. So we have the 4 cosets there. Okay. 4 coset. Now actually you see here how many subset you can construct with that. For each subset you have the 4 coset. For each subset you have the 4 coset. Is it clear? For the cube root, fourth root of unity, we have the 4 element on the G. Now you consider a subset of that G, that is the H. Okay, now you can construct a coset HA. Since we have the 4 elements, so a number of A is 4 there, so you can construct 4 coset in the form of HA. Similarly, if you consider the other subgroup, in fact, subgroup of G, then again for that particular subgroup, you can get the 4 cosets there also. And that are the right coset. Similarly, you can get the left coset also. Now I think it is a little bit clear to you.
Yes, sir.
Okay. So once it is clear, so how will you define the left coset? Left coset of H in G
AH.
generated by A belongs to G is given by, how can you write it? AH or AH, that is equal to A into H, that is H belongs to, okay. So this is your left coset. It is a left coset. And don't think that HA equal to AH, okay. Because always we are using the two one terms abelian. Okay. So when it is abelian, when we have HA equal to HA, AH equal to HA, then it is abelian. If it is not possible, then we have we can't say that AH is equal to HA. If it is abelian, then we can say that the two left and right cosets are same. Okay. So from there you can define a particular type of subgroup that is called the normal subgroup. Normal subgroup. So what is the normal subgroup? A subgroup H of a group G is said to be subgroup if A inverse H A, and okay, that is the subset of H for all or for every A belongs to G. Okay, so what is the meaning of this? So equivalently you can equivalently we can say that H is the subgroup, H is normal if AH, left coset, is equal to right coset, and it is valid for all A belongs to G. Is it clear?
Yes, sir.
So we have lots of theorems related to this, but we are not going to just prove this one. But you should know what is the coset and what is the normal subgroup. Normal subgroup means if AH is equal to HA, then it is said to be normal subgroups. Okay, and we have already priorly defined what is AH and HA. AH and HA are the special type of set. That set is called the coset. Okay, now we have okay, next class we will discuss this. Order of a group. Order of a group means what? Order of 5 minutes. I will take 5 minutes only. Order of a group. So what is the order of number of elements of a group is called the order of the group. Okay. Number of elements of a group is called order of that group. Group, order of element of group and order of group. Okay, and it is denoted by order of G. Okay, so if it is the 4 elements, then order of G is equal to 4. But we have the very important theorems. Okay, that is called the Lagrange's theorem. Lagrange's theorem. What is the Lagrange's theorems? The order of each subgroup. Very important. The order of each subgroup of a finite group. So mark it, of a finite group. Okay. The order of each subgroup of a finite group. Suppose I would say G. Each subgroup. H is the any subgroup, but all the subgroup. The order of each subgroup of a finite group G, you can say, is a divisor of the order of. Is it clear? This is very important theorem. Okay, order. This is the order of a group. Order of group, that means number of elements of that group, and or the order of each subgroup of a finite group G is a divisor of the order of a group. So one thing from here it is clear. Suppose we have a 4 elements, cube root, fourth root of unity. Okay, then if you are considered the any subgroup, okay, so that subgroup must be of order 2. Okay, order 4, that means the group itself, or 1, like this. If you are considering a group of order 6, okay, then the subgroup containing 1, 2, or 3, okay, that subgroups are the, sorry, that are the subgroup. That means if you are considering any subset of that, and cardinality of that subset is the divisor of the group, then we say that it is a subgroup. Otherwise it is not a subgroup. Okay, but one more thing, very important thing, is converse is not true. Converse of, this is the note, converse of Lagrange's theorem is not true. Is it clear? Converse, that means the cardinality, if you are considering G as the fourth root of unity and the cardinality of the subgroup is 2, okay, then it may be subgroup, may not be subgroup, may be subgroup, may not be a subgroup. And priorly we have seen that we have a subgroup of the fourth root of unity, okay, that is what, I and minus I probably, sorry, 1 and I, 1 and I, these are the two, 1 and I, that is the subgroup. So if you are considering 1 and minus 1, although it is a subset, okay, but it should not be the subgroup of this. So if H is the subgroup, then the cardinality or the order of the subgroup H, okay, the order of the subgroup must divide the order of the G, but the converse is not true. That means it doesn't mean that if the order of H divides the order of G, that means H is a subgroup. It is not true. Is it clear what I'm saying?
Yes, sir.
Oh,
Yes, sir.
okay. And one very important note is here. Second note, it is very important. If if I write n be the order of a finite, always you are considering the finite group, and uh, A be any element of G, then E is the identity element. If n is the order of the finite group, n is the finite group or the, and A be the any element of G, then A to the power n is always E. Is it clear? It's very important point.
Yes, sir.
And E is the always remember this one. Always remember this one, and next class just remind me, I will show you what is the quotient group. Quotient group is very simple, and then permutation group. So the next class we will go through this quotient group and the permutation group. Okay, but keep it into the mind, this last one is very important. Okay.
Okay, sir.
Any query?
Okay, sir.
Any query?
No, sir.
Okay.
Thank you, sir.
Okay, you
Thank
may
you,
leave.
sir.
Thank you, sir.
Okay, bye.
Thank you, sir.